Let's talk about an SVD part of our project. Actually, an SVD it's also a way to describe the change of peak frequency in a time. We want to build such a method to represent our matrix as this formula, where the U is a matrix based on a left self vectors, singular vectors. The E matrix is a matrix with the singular values on the main diagonal, and we transposed its transposed vector of our eigenvectors of a matrix A transposed. So how we get a singular values? We get singular values by first we build a matrix A transposed, and we got an eigenvalues of this matrix, and the singular values it's a square root of eigenvalues. And then for a matrix U we will calculate also we would calculate an eigenvectors of this matrix. I will call them Vi, and then single vector for a matrix U will be built as A multiplied by the vector V divided by a singular value. So we have represented such a way a matrix. As I have mentioned, the E is just a diagonal matrix, and V transposed is a matrix that is built on an eigenvalues of A transposed matrix, but transposed. So we have built, and how is related to our topic of our project. This method is widely used for an image compression. For an image compression, we use such a variant of SVD as reduced SVD form. Reduced SVD, it's we can get singular values which is equal to 0, and by them will be change our matrix U and V, because we also would get some eigenvectors. But in a reduced SVD we ignore singular values that is equal to 0. We just save the singular values that is not equal to 0, and from this our matrix would become smaller and the image compression would be done. How it works, we save the largest one. Actually we can say we can save the so many as we ask, and from that the largest one we got the image compression. In our topic we will also try to compare a wavelet transform and an SVD. A wavelet transform, I was already talk about it in a previous part, and an SVD I have represented you now. So also in this project I need to cover how would we connect them. We would use such a function that is called PSNR. PSNR it's a function that compare the starting image to the compressed one, pixel by pixel. And in this way, we would try to find an equal PSNR value for each our method. That we would see in our project that our compressed image would be different, but we can say that the value of compression is nearly equal. So what also we want to say about an SVD and about maybe wavelet a bit. An SVD transform is strong because it's ignoring noises. It's just do not affect this method. It actually, the SVD at all can be using for a rotation, a V-transposed matrices, a scaling, what we have also done in our laboratory work number 3. So we would see that these methods are similar in some cases, but they give us a different image in an outcome. So we would understand in which cases they are better. For example, a wavelet transform, it's better when we want to save some details in some direction, because as I have said, the basis matrix which is based on, but an SVD method, it's actually like make an image equally blurred for each part, and actually it's even the most common variant that we use for blurring and compressing the image. So like that.